All right. Okay, this is the last example. Then we're going to go through one more practical example. Then we're going to call it a day. So, so this third hour will not be a tutorial. That will take place the next class. I want to make sure you have enough AM theory before we actually go and solve questions. And then I should be able to finish the rest of the AM theory hopefully by next class and not the next class after that. Okay? All right, so let's take a look at another example. So instead of using a message where it was symmetric, it was a cosine wave that was plus minus, with an amplitude of a sub m, we're going to take a look at another message signal now where it's quite symmetric. So in this case, the highest peak in terms of the positive would be 0.8, and then the lowest would be minus 0.3. Okay? If we were to perform amplitude modulation on this, remember you're taking your message, you're adding a DC offset. So in case the DC offset is going to be up here, right? This is a DC offset. And then you're going to modulate it by cosine wave. So that increased height will be multiplied by cosine wave, and that's actually what it looks like. Okay. So let's actually take a look at what the performance measures are. So let's take a look at calculating the modulation indices. Take a look at modulation indices, and take a look at what happens with this particular signal when looking at the modulation indices. Okay. So first, let's take a look at the parameters. So m sub p is the largest value in terms of the absolute of the actual message that you find. In this case, it's 0.8. That makes perfect sense. And then if you want to figure out what the largest value is for AM max, all you're doing is you're taking a carrier and you're adding it with the most positive point in your message. In this case, this is 0.8, and that's what we get. Okay. In terms of the minimum, you're taking the lowest possible point in your message and you're adding it with the actual message. Okay. And that's what's happening here. So this is technically plus minus 0.3, right? But it's subtract anyway. So you're taking the lowest possible point and then you're adding it on top of the carrier, and that's what a sub min would be. So this is actually what it looks like. Okay. So let's go ahead and calculate all the performance measures. So if you want to calculate the modulation index by itself, it's actually quite easy. This is the first definition. You take m of p, which is 0.8, and then you divide it by the height of the carrier, which is a sub c. That's great. So if you actually want to take a look at the modulation index in the second definition, you take the large, a sub max, which is AC plus 0.8, and then a sub min, which is AC subtract 0.3. So if you have AC plus 0.8, subtract AC, let me see here. So subtract, 0.8. What the hell? Why is that 0.55? That doesn't make any sense. Okay, so actually that's a typo. Okay, so AC, so we have A of C plus 0.8. Okay, subtract A of C minus 0.3. Okay, these ACs cancel, and you should actually get 1.10. Okay, 1.1. It's actually, I don't know why it's 0.55 there. These are actually not my slides. These are somebody else's, actually Professor Zeytinoglu's slides. So if you actually do the subtraction, it's actually, oh yeah, so 1.1, actually no, it's not an error, I'm sorry. So it's 1.1 divided by 2A of C. In this case, you get 0.55. Okay, I'm not imagining things. Okay, the actual slides are fine. Sorry about that, I had a brain fart for a moment. So 1.1 divided by 2 is actually 0.55, so that's what we get here. Okay, so if you want to figure out what the positive modulation index is, it's A sub max subtract A of C. Okay, so in this case, you have A of C plus 0.8 minus A of C divided by A of C. Okay, so this cancels out, and we're left with 0.8. That's totally fine. And then we have the negative one now, right? So here we have A of C subtract A of C minus 0.3 divided by AC. So these cancel, plus plus becomes a positive, minus minus becomes a positive, sorry, and this is what we get. Okay, so you're probably noticing now that when you calculate the modulation index using the first definition, compared to the second definition, they're different. The results are quite different. Why is that the case? Well, let's actually take a look at the next slide. If you notice, if you remember from the first example, all of these values, so the modulation index, the negative, and the positive and the negative, they all matched up. But in this case, they don't match up. Okay, so why is that? The reason why is because if you take a look at the message signal, you'll see that it's not symmetric. So the message signal is not symmetric. So remember, if you were to take the message signal, if you were to put a mirror running the horizontal axis, the positive, the top, and the bottom should be a mirror reflection of each other. If you take a look here, the negative portion here is not equal to the positive portion. Like it's not a mirror reflection of each other. So this is actually not symmetric. So this happens when your message signal is not symmetric with respect to the horizontal axis, and that's why it's happening. Okay. Also, if you take a look here, when you're defining the modulation index, this is using the largest amplitude, so the largest, amplitude, I guess absolute value. Okay. And this here is just using, this is reporting it as the average, right? So what you're doing here is basically mu minus u plus divided by 2. So that's actually what's happening here. Okay? Sorry. So this is just the average of the two. So one of the definitions takes a look at the largest amplitude. The other one is the average of the negative and the positive modulation indices. So which one do you actually use? Well, I guess it depends on your preference. Because in this case, you have a message signal that's not symmetric. You just have to choose whichever one that you believe is most appropriate for your application. Okay? So results from the two definitions between the modulation indices as well as these two values, the positive and negative, right? They are not equal to each other. So this means that the message signal is not symmetric with respect to the horizontal axis. So when you take a look at the first case, it's just the cosine wave. If you were to put a mirror right on the horizontal axis for the message, you'll see that the top and the bottom are symmetric. So in that case, everything's going to match up. But in this case, where the message signal is not symmetric, then you get these conflicting pieces of information, and that's not good. Okay, here's the last tidbit I have before we go on to just one more small topic, which will just take a couple of slides and I'll let you guys go. This is talking about carrier and sideband power. The reason why we want to talk about this is because we want to take a look at how efficient amplitude modulation is when you're transmitting a signal over a channel. Okay, so definition: G bar of t represents what's known as the time average of G of t. Okay, so what this means in particular is, so G of t, and then let P of x be the power delivered by the signal. So what this is talking, so in terms of time average, the definition, okay, is the following. So this is assuming this is a periodic signal. So what you're doing here is you're assuming a periodic signal, and the definition of the time average, all right, is defined as, so limit as time approaches infinity, 1 over t, going from t over 2 to t over 2 of dt. Okay? Just want to double check if I got this right. I can never remember the formula. I'm just going to double check. Let's see here. Sorry, just give me a moment. Yes. Okay, that's good. So this is what is defined as the time average. So it's 1 over t, and then, so assuming a periodic signal, so this would be the period. Okay, so this is 1 over t, and then the integral from minus t over 2 to t over 2 of the square root of the waveform. So this is what is the time average. Okay, so usually we consider the load to be a unit load if you want to take a look at the actual power. So unit power is when R is equal to 1 ohm, I guess. All right, so we also take a look into, the reason why you consider it as unit power is because as you start increasing the load, then what's going to happen is that the power should decrease as much. So you're using this as kind of like a standard normalized measure, and then as you start increasing the load, you would expect the power to decrease by a factor of that much. Okay, so this is what the time average would be. So this is what the definition would be. So you're taking the integral of the square root of the actual waveform and going between half the period, from minus to plus, and then you're dividing by 1 over, you're multiplying by 1 over t, and then you take the limit as t approaches infinity. That's the definition. Okay, so consider the amplitude modulated signal with a message signal that has a bandwidth of b of m. So what this means specifically is you have a message signal like this with the largest component at b of m, and then we'll call this f, I guess. The frequency, we're taking a look at it in terms of hertz. Okay, so this is what the spectrum would look like, m of f. Okay, so when we expand this out, remember this was equal to a plus m of t cos omega ct, right? So all we're doing now is we're just expanding out this expression to get a summation of these two terms. Okay, so this here is the carrier, of course, and then these are the sidebands, or what is contained in the actual message, okay, or the actual message signal components. So what we're going to do now is we're going to take a look at how to calculate the efficiency of amplitude modulation. So we're going to compute the power for an amplitude modulated signal, which we'll call P of psi, and we're going to express it in terms of the carrier power and the sideband power. So we're going to actually compute what this would be. Okay, so here we go. So this is your amplitude modulated signal. You have a summation of 2. And then what we're going to do is we want to calculate the power. And so what we're going to do is we're going to do it over a unit load. Okay, so we're going to do it, so a unit load. Okay, so R is equal to 1 ohm. Okay, so what's happening here is that you want to square this, right? So because if you want to figure out what the power would be, you have to square it, and then you have to find the integral, right? So in this case, we have A of C, M of T, sorry, not A of C. This would be A of C cos omega CT plus M of T cos omega CT squared. And when you actually carry out this multiplication, you get what's below here. Okay? I'm not going to do that for you. I'm going to leave that for you as an exercise. But when you expand out this is a basic, perfect square. You expand this out to be like that. Okay. So what's happening here is that we have a summation of 3 terms. So what you can actually do is you can actually find the power of each of these individually. So if you want to figure out what the power of the signal is, right, you can just find the power of each of these individually, which is totally fine. Okay? So we're going to call this P of 1. We're going to call this P of 2. We're going to call this P of 3. Okay? All right. Where this comes from is very simple. Okay? Remember that you can express this as 1/2 plus 1/2 cos 2 omega CT. Okay? So then we can actually expand this out, and you'll get A of C squared and so on. And then when you find what the integral of this is, right, over a period, okay, remember that this here, this is an even function. Not even function, it's an even function, yeah. So remember, when you find the integral of an even function over a period, that integral goes to 0, okay? So this integral goes to 0. Okay, so what's left is just this guy, which is what we have here. Okay, so when you have an integral with respect to cos, if you're doing it over one period, as long as you are doing it over you're doing it over the proper period, even though if it's 2, you're still doing it over, the one period, that final integral becomes 0. So what you're left with is just AC squared over 2. That's nice. Okay, so that's where the first term comes from. Now we want to do the second term. This here is P of 1. Okay, the second term is very simple. So assuming that your carrier frequency is much, much larger than the bandwidth, which that's usually the case, that's fine, okay? We can also do the same thing here where you have 2A of C, M of T, and then this becomes 1/2 plus 1/2 cos 2 omega CT, right? Okay, so when we expand this out, these two go, those two goes away with that and that. So you're left with just AC M of T, right? And then cos. So what's going to happen here is that, let's see here. We're assuming here, so this is assuming message is symmetric. Okay? So if that's the case, so the message is symmetric, this means that it's even. So if you were to try to find the integral of this, so you're going integral from minus t over 2 to t over 2 dt, what's going to happen is that because this is even, then this integral goes to 0, and then this one we know goes to 0 as well because of the cosine term. So everything goes to 0. So this goes away, all right? Because we're assuming that the message is symmetric. So that second term goes away. That's totally fine, okay? Then we're going to take a look at the next one, all right? In this case here, we see that we have m squared of t. So m squared of t is no longer symmetric. We're just taking a look at m of t's. So remember, what's happening here is we can split this up so that this becomes m squared of t, and then 1/2 plus 1/2 cos 2 omega CT, right? Actually, let me make this a little bigger. M squared t, 1/2 plus 1/2 cos 2 omega CT. Okay, so remember that cos is an even function, right? So if you were to take the integral of this, sorry, I don't know how to use colors, the integral of this, okay, and then we did dt here. This goes away, right, because it's even. So all we're left with is this guy, right? When you integrate, and then you have 1 over t, and when you take the limit, what's going to happen is that you're just, well, you're left with whatever this power is divided by 2. So that's what this here is. So this is the integral, right? So limit as t approaches infinity, 1 over t, and this is minus t over 2 to t over 2 m squared. So that's what this is. We don't know what that is because we don't know what the actual message is, but that's the definition. So we're left with just this term by itself. So whatever the message power, the time average of the message is, that's what you get. So that term goes away because we're multiplying by cos, that's even, but we're left with this term, and whatever that is, we leave it to evaluate. So that's what we get here. Okay, so that's 1, 2, and 3. So finally, if you want to figure out what the total power of the AM signal is, right? So we have AC squared over 2 from before, so this is P of 1. This is P of 2, which is 0, and then this is P of 3. So the total power is just adding all these together. So this would be the power of the carrier. So this is the carrier power. Okay, and this is the sideband's power. So that's the total power for the AM signal. So you're taking the carrier power plus the sideband power. Okay, and that's what it is. Okay, so observation. Any power used to transmit the carrier is wasted, and we'll talk about that in a little bit. But if you are using amplitude modulation and then you have a carrier that you're adding on top of your message signal, the power that you're using to transmit that carrier is unfortunately wasted. So what that means is that the efficiency, or how much power you're putting into the system compared to what you see in the output, is actually very small. The efficiency is quite small, and that's actually very bad, but still AM is still a technology that's used very often. Okay, so the sidebands are a function of the message and carry all the information in the message. So what we want to do is we want to maximize the sideband power. So what you're doing here is that you want to make sure, if you want to increase the efficiency, what you have to do is you have to make sure that the power contained in the message signal is as large as possible in order for you to make sure that the efficiency is as high as possible. So that's what it means by maximizing the sideband power. Okay, so the power efficiency is finally the following. So what you're going to do is you're going to find the ratio between the useful power, or the message power, or the sideband power, okay, divided by the total power. So this is actually what the efficiency is. So you're taking a look at the power just generated by the messages itself, divided by the total power, which is the message and the carrier. Okay, so that's what the power efficiency would be. Okay, so this is my last example, and then we're going to call it a day. All right, so we're going to take a look at the power efficiency for just a single tone signal. So the message signal is just a cosine wave with an amplitude of A of m, and the carrier is another, it's another cosine wave with a carrier frequency. You have to make sure that the carrier frequency is much larger than the message, and it's multiplied by some constant, which is A of c, which is the height of the carrier. Okay, and the modulation index is defined as m sub p over A of c, right? And in this case, m sub p is just A of m, which is why we get that. Okay. So if you want to figure out what the sideband power is, all you're doing is you're just taking the power of the message, dividing it by 2. So because this is a cosine wave, because m of t is a cosine wave, if you remember from what we did before, if you take this squared, we get a squared, a of m squared, and then you have half plus half cos 2 omega ct, right? And if you remember, if you wanted to find the actual power, this goes to 0, so all you're left with is am squared over 2, right? So that would be the actual power of the sideband. Okay, so that's in general. So if you want to figure out what the power is for a single cosine wave, it's just simply the amplitude squared divided by 2. So that's just something that you want to take a note of. So that's the actual power, okay? So then what you want to do now is you want to figure out what the useful power is. So you're doing that squared divided by 2, and then you have to divide it by 2 once more, okay? And in this case, so power is, this is am squared divided by 2, and then you have to divide it by 2 once again. Sorry, because you have this guy, right? So in this case, you get am squared divided by 4. And then A of m is equal to what? It's equal to mu AC, okay? So we have am squared divided by 4. In this case, we get mu squared, AC squared divided by 4, and that's where this comes from. Okay, and the carrier power is very simple. It's just AC squared divided by 2. I got a couple more slides and we're done. All right. So the modulation index is the case. So this is the sideband power. So what you can do is you can actually, so this is what is known as Parseval's theorem. If you actually take the Fourier transform and you actually square up all the amplitudes, it actually equals the actual power itself. So this is so if you actually take the when you have the actual sideband power, remember this is your message signal and it's modulated. Sorry, it's modulated plus minus, f of c. So remember this spectrum, it looks like this. You have minus fm and fm here. right? And if you modulate it, then you're going to get 2 copies. So the first copy is over here. So this is for plus FC, and then you have another copy over here, minus FC. And when you add up all these components squared, if you actually take all the heights, square them, and add them up, you actually get this guy over here, which actually makes sense. The actual carrier power, again, is very simple. All you're doing is you're just taking the actual heights for the carrier. Remember, the carrier is defined as, AC cos omega CT, right? And then what you're doing here is you're modulating that left and right? So in this case, you're just not modulating, but you're getting 2 impulses, right? So you have one defined here and one defined there. And if you actually take each of the amplitudes, square it, add it up, you actually get that, which is fine. Sorry. So the power efficiency is very simple. So what you're going to do is you're going to take P of S, which is this guy over here, right? So this goes here and here. And then you're going to divide it by the total, which is the carrier plus the actual sideband power. So this goes over here. Okay. So when you actually add this up, so what happens is that you can actually let's see here. So you have UAC squared over 4. If you rearrange this, you can actually factor out an AC squared. Okay. So in this case, you can actually factor out an AC squared from top and bottom. So you get mu squared over 4 divided by 1 over 2 plus mu squared over 4. Okay, you can factor that out. These cancel, and then what I can do is I can multiply up and down by 4. Okay, so if I multiply by 4 here, my 4 here, these cancel, this cancels, you factor this in, this becomes a 2, right? And that's why you get that here. Okay, so you actually get your power efficiency in terms of the modulation index. So what this means is that if you want to make sure, remember that the modulation index varies between 0 and 1. Okay, so the largest efficiency you're ever going to get is when mu is equal to 1. So that's actually 1 over 2 plus 1, which is 1 over 3. So the maximum efficiency you're ever going to get with amplitude modulation for the single case is 33%, which is pretty bad. Okay, so given the power efficiency, which is over here, so if you want to use an envelope detector, you have to make sure that the index is between 0 and 1, of course, right? So the maximum power efficiency you're ever going to get is at mu is equal to 1. So if you substitute 1 in, you get 1 over 3 or 33%. So that means that if you transmit 3 watts into your system, the output power you're going to get is 1 watt. So you're actually taking your input power and you're dividing it by 3. Which is actually pretty bad. 33% efficiency is actually not very good. Okay, this is actually yep. So I have 2 more slides and we're done. Okay, so in terms of broadcasting standards, when you take a look at the the Canadian Radio and Television Commission, or they actually control how radio signals are being transmitted over the air. They actually have the following standards when you're taking a look at broadcasting in AM. So the assigned carrier frequency, so what the carrier frequency is that it tells you which station in your radio to tune to. So, if you wanted to listen to Fan 590, the carrier frequency is 590, kilohertz. Or if you wanted to listen to, AM 640 when you want to listen to traffic, the carrier frequency is 640 kilohertz. So the actual carrier frequency is used to figure out which station you want to tune to. Okay, so that's what the carrier frequency is. And it ranges between 540 and 1600 kilohertz in 10 kilohertz increments, which actually makes sense. If you actually try to turn your dial, you'll see that it jumps every 10 kilohertz. Okay, the channel bandwidth is 10 kilohertz, so that means that at 540, the bandwidth of your signal is going to be between 535 and 545 kilohertz. So that's 10 kilohertz. And also you have the carrier frequency stability, so that means that the delta F that we talked about in terms of amplitude modulation is plus minus 20 hertz. And the percentage modulation, or the mu, right, is going to be either bigger than 0.85, so in terms of percentage, and less than 0.95. So that's what it means by 85 to 95%. So the maximum modulation values in terms of the plus and minus is actually this. So you can actually go above and below. It depends on your situation. So the frequency response is, okay, so the actual message signal you want to carry, so it should be contained between 100 and 5 kilohertz. So this is the bandwidth of the message. Okay, and harmonic distortion and maximum license powers, I won't go through that, but this means that the carrier power should be at least 50 kilowatts. I won't go through this. This will go later. I won't talk about that until later, but I just want to give you some standards here. And this is my last slide. All right. So This is a comparison between double sideband suppressed carrier and double sideband large carrier. This is the last slide, I promise, and then we'll go. All right, so given a baseband modulating signal, your message signal MFT with some message bandwidth B of M, right? We have two amplitude modulation schemes so far. So we have double sideband suppressed carrier and double sideband large carrier, or A of M. And this is a comparison table of what we're taking a look at in terms of the efficiency. So in terms of the actual bandwidth, okay, it occupies twice the bandwidth, the message of the bandwidth, the message bandwidth. That actually makes sense. This has no carrier, but the amplitude modulation does, right? DSB-LC. And then in terms of demodulation, you need a coherent detector. And this one, you can use an envelope or coherent if mu is greater than 1, if you wish. And then the power efficiency, it's going to be 100% because you're actually not transmitting the actual carrier, right? Remember, the efficiency is equal to the power of the sidebands divided by the power of the sidebands plus the power of the carrier. And because there is no carrier in DSB-LC, right, this means this is 0, so you actually get 100%. So because you're not actually performing, you're not actually transmitting the carrier, you get 100% efficiency, but you need coherent demodulation, so the electronics are more expensive. So you're going to get a nice clean signal, but at the same time, you're going to have a receiver which will cost a lot of money. So do you choose a situation where you have a receiver that is cheap, but you're able to, receive as many signals cheaply, or do you want to have a clean signal, but the receiver is quite expensive? So it's just a little bit of push and pull. Okay, that's my last slide, all right? So I'll let you guys go now. Next week, we're going to start the AM tutorial. I'm going to do some questions, and then we'll finish up AM for the last half of the class. Thanks for coming.